Hey everyone! Looking for a super quick rundown of the entire chapter on sets? Well, you're in the right place. Over the next few minutes, we're going to blitz through all the key concepts you need, from the very basics all the way to solving those tricky problems. All right, let's dive right in. So, here's what we're going to cover. We'll kick things off by figuring out what a set actually is. Then we'll see how to write them down. After that, we'll take a tour of the different types of sets, see how they can fit inside each other, and learn a few operations we can do with them. And to wrap it all up, we'll use everything we've learned to solve a classic problem. Let's get to it. All right, first things first, what exactly is a set? Before we jump into anything else, we have to nail down this one core idea. Okay, so the textbook definition is a well-defined collection of objects. Now, collection of objects is pretty straightforward, right? But the secret ingredient, the really important part, is that phrase well-defined. So what does that really mean? It means there's no room for opinion. The rule for being in the set has to be totally clear, with no debate.
And here is the perfect way to see what well-defined really means in practice. If I ask you for the 3 most beautiful girls in your class, is that a set? Nope, not at all, because beauty is subjective, right? Your list would be different from your friend's list. But if I ask for natural numbers less than 10, everyone on Earth is going to give the exact same answer. 1, 2, 3, 4, 5, 6, 7, 8, and 9. That is a well-defined set.
Okay, so we got a handle on what a set is. Now, how do we actually write one down? Well, there are 2 main ways to do it. First up, you've got roster form, and honestly, it's just a list. You literally list out every single member of the set. For that equation on the screen, the solutions are -2 and 1, so we just write them out inside the curly braces. Easy. The other way is called set builder form. Here, instead of listing everything, you just state the rule that an element has to follow to be in the set. So we'd say A is the set of all numbers x, such that x is a solution to this equation. It's 2 different ways of saying the exact same thing. So now we know what sets are and how to write them. Let's go on a quick tour of the different types you're going to see. Think of these as different flavors or categories for sets. First, you have the empty set. It's empty. 0 elements. Then there's a singleton set, which has just one lonely element inside. A finite set is any set where you could eventually count all the elements, like the vowels. An infinite set, you guessed it, goes on forever, like all the natural numbers. And finally, you have equal sets. This is important. They have the exact same elements, but the order doesn't matter at all. Okay, you'll want to pay close attention here, because this idea is super important. Sets don't just exist in a vacuum. They can actually be related to each other, and a lot of the time, they exist inside of other sets. And that brings us to the idea of a subset. The best way to think about it is like one of those Russian nesting dolls. If every single thing in set B is also in set A, then we say that B is a subset of A. It's just a smaller set that's totally contained inside the bigger one. Now let's take that idea a step further. What if we took a set and we found every single possible subset you could make from it? I mean, everything, from the empty set all the way up to the set itself. If you gather all those little subsets together and put them into one new giant set, you've just created what we call the power set. Let's walk through this together. Say our set is just 1, 2. To find its power set, we start systematically. First, the subset with 0 elements. That's always the empty set. Then, all the subsets with just 1 element, so 1 and 2. And finally, the subset with both elements, 1, 2. The power set is just a new set containing all 4 of those options. And here's the cool part. A little shortcut. You don't have to list them all out every time. There's a magic formula, 2 to the power of n, where n is just the number of elements in your original set. So for our set 1, 2, it had 2 elements. That means its power set has 2 squared, or 4 members. And that's exactly what we found. So, just like you can do things with numbers, add them, subtract them, you can also perform operations on sets. This is how we combine them or see what's different between them. Let's run through the big 3. First is the union. Think of it like a union. It brings everyone together. It's a new set with all the elements from both of the original sets. Then you have the intersection. This is just the overlap. What do the 2 sets have in common? And finally, the difference. A minus B gives you what's in A after you take out anything it shares with B. Last one is the complement. Now, for this to make sense, we need this idea of a universal set, which is basically the big picture context, everything we're talking about for a given problem. The complement of set A is just everything in that universal set that is not in A. It's everything outside of A. So we have all these definitions and rules, but how do we actually use them to solve problems? Well, the single best tool in our toolbox is the Venn diagram.
A Venn diagram is pretty much just a map for your sets. That big rectangle is the universal set, our whole world for the problem. Each circle inside represents a set. And the really useful part is where the circles overlap. That overlap shows you the intersection, what the sets have in common.
Now, when you're solving word problems, this formula right here is your best friend. If you want to find out the total number of things in the union of two sets, you can't just add the number in A and the number in B. Why not? Because you'd be counting everything in that middle overlapping section twice. So you add A and B, but then you have to subtract that intersection one time to get the correct count. Let's see this in action. We've got 400 people. First step is to find out how many people like at least one of the juices. That's the union. So we use our formula, 100 apple drinkers plus 150 orange drinkers minus the 75 who like both. That gives us 175 total people who drink juice. Now, to find who likes neither, we just take our grand total of 400 people and subtract that 175.
And there it is, 225 people. That's our answer. That's how many people in this survey like neither apple nor orange juice. See how powerful that simple formula is?
All right, your turn. Time to put what you've learned to the test with this classic three-set problem. Now, here's my big tip. Draw the three overlapping circles and always start by filling in the number for the dead center, the part that belongs to all three sets. Once you have that, you can work your way outwards. Your goal is to figure out how many people like only product C. Go ahead and pause this explainer, give it a shot, and then post your answer down in the comments. Thanks for hanging out with me for this whirlwind tour of sets.